I'm here with Daniel West from Kyocera AVX, and Daniel has a bunch of brand new capacitor technologies displayed for us, and he's going to talk to us about what goes on behind the scenes with some of these. Daniel, what you get here is actually some pretty cool new materials that are allowing you to do a lot of interesting things. How about telling us about that?
Yes, sir. New materials, new ways to process them and refine them, making sure that, with logistics and everything, keeping them segregated so there's no contaminations. For ceramic capacitor technology, we're working on some brand new formulas. We have very small MLCCs, EIA case size 01005, so very small, can almost be considered an inhalation hazard, they're so small. Very hard to work with and mount. Volumetric efficiency benefits that we get there is very large. And with that, we have to work on very robust formulas because we still need to maintain temperature performance, high voltage performance, and have that capacitance stability that essentially the engineers and the customers are looking for in that technology. We have a 3-terminal capacitor. It's an 0402 case size, great for broadband EMI filtering.
I see you got some tantalum capacitors here about the size of the end of a pencil tip. Talk to us about that.
Yes, the new developments with tantalum electrolytic capacitors would be, again, working with our newer materials, newer processes to work, again, to make a volumetrically efficient design. And that means working on brand new lead frames. We have a tantalum pellet that needs to be attached with a metal lead frame. That adds inductance into our circuit, which is undesired, keeps it working at a higher frequency range. We have a military qualified device that has a leadless frame. And the way we can do that is with advanced encapsulates, we isolate it from the environment so we don't need as big of a lead frame. And it's actually leadless and it's very small. The new hot thing now is supercapacitors. They're also called gold capacitors, ultra capacitors. They use a completely different material system than we've seen traditionally in capacitors. And it's approaching energy levels of batteries. And so we have a very large supercapacitor module here. It's 48 volt, 165 farads. So it is very large, can deliver massive amounts of power, but it can also charge with massive amounts of current as well. So for robotic warehouse, robots in warehouse, anything that is cradle charged can quickly be charged up with a supercapacitor bank. The batteries on windmills, you need motors to turn the fan blades so that we get the most advantageous amount of wind. And typically you would use a battery system. But when the batteries get old, it's very expensive to send someone up there to replace the battery. It's very dangerous. If you use a supercapacitor bank, the amount of times that you would need to replace that system would decrease by far. So we're seeing supercapacitors enter also the energy harvesting, energy recovery markets as well, in addition to peak power.
Daniel, we've got a demo here that's kind of interesting.
This utilizes our film technology. It's used for very large power conversion where where safety is a priority. These capacitors actually self-heal. If we see a hot spot, that hot spot, whether it's due to an overcurrent, a surge, that part of the electrode would be isolated. And that is the key benefit of film capacitors. Whether you want a DC link capacitor for electric motors, electric vehicles would make use of film capacitor technology, or a large solar farm where you need to switch the DC power coming in from solar to an AC to feed that energy back into the grid. Because it self-heals, it's great for those applications. But if we need it to work into a higher frequency range, we run into some issues where we need to accurately characterize the material and how it's formed in here. We can't see inside it, but it's essentially wound and there's multiple elements. We need to magnetically and thermally characterize these material sets, and we have robust software. We have robust sets of data from historical designs built into CAD/CAM models. And that's how we come up with unique designs for bus bars, and the terminations and the actual internal geometries of the film capacitor.
Thank you for that, Daniel. It's obvious why capacitor technology is an important part of power circuitry. Where can our viewers go for more information if they want?
They can go to www.kyocera-avx.com for more info on our products, and also software and online simulation tools.